The universe contains roughly 200 billion trillion stars. Around each of those stars, planets likely orbit, many in zones where liquid water could exist. By the most conservative estimates, billions of Earth-like worlds should be scattered throughout our galaxy alone. Some of those worlds formed billions of years before our own planet even existed. Life should be everywhere. Advanced civilizations should have spread across the cosmos long ago. Yet when we look up at the night sky, we see nothing but silence. This is the Fermi Paradox, and it's not just unsettling. It's scientifically inexplicable. The question emerged during a lunch conversation in 1950 at Los Alamos, where some of the most brilliant minds of the atomic age had gathered. Enrico Fermi, the physicist who helped unlock nuclear energy, was discussing the possibility of alien civilizations with colleagues Edward Teller, Herbert York, and Emil Konopinski. The conversation touched on the vastness of space, the number of stars, the likelihood of planets. Standard speculation about extraterrestrial life. Then Fermi stopped mid-thought and asked a question so simple it seemed almost trivial. Where is everybody? For words that would haunt science for the next 7 decades. Because Fermi wasn't just wondering whether aliens exist. He was pointing out a mathematical impossibility. If intelligent life is even remotely common, the galaxy should be teeming with evidence of it. Radio signals, megastructures, probes, something. The Milky Way is roughly 10 billion years old. Earth formed only 4.5 billion years ago. That means countless star systems had a 5 billion year head start on us. Even traveling at a fraction of light speed, a single civilization could colonize the entire galaxy in just 10 to 50 million years. That sounds like a long time, but it's a rounding error on cosmic scales. It's less than 1% of the galaxy's age. So where are they? The paradox didn't appear in scientific literature until 1963, when Carl Sagan formalized it in print. But the question itself proved impossible to ignore. Because the math keeps getting worse. In 1995, astronomers discovered the first exoplanet orbiting a sun-like star. That single discovery opened the floodgates. We now know of thousands of worlds beyond our solar system, and statistical analysis suggests something staggering. At least 25% of stars host rocky, Earth-sized planets in their habitable zones. 1 in 4. That's not a rare cosmic lottery. That's a pattern. In early 2026, astronomers identified a super-Earth called GJ887d, orbiting in the habitable zone of one of our nearest stellar neighbors, just 10.7 light-years away. It's only the second confirmed habitable zone planet within 10 light-years of Earth. Another recent discovery, in the GJ251 system just 18 light-years distant, revealed yet another potentially habitable world. These aren't speculative candidates in distant galaxies. They're practically in our cosmic backyard. The numbers scale up fast. The Milky Way contains over 100 billion stars. If even a tiny fraction host life-bearing worlds, we're looking at millions, possibly billions of planets where life could have emerged. Some of those worlds are ancient, formed when our galaxy was still young. Life on Earth took roughly 4 billion years to evolve from single-celled organisms to a species capable of radio transmission. That timeline isn't unusual by cosmic standards. It's a geological blink. Which brings us back to the central horror of the Fermi Paradox. We should see them. We should hear them. The galaxy should be absolutely crowded with evidence of intelligence. But we detect nothing. In 1961, astronomer Frank Drake attempted to quantify this problem by creating what's now called the Drake equation. It's been called the second most important equation in science, and it breaks down the question of alien civilizations into manageable variables. How many stars form each year? How many have planets? How many planets are habitable? How many develop life? How many evolve intelligence? How many build technology capable of communication? How long do such civilizations last? The equation looks deceptively simple. Multiply those factors together, and you get an estimate for the number of detectable civilizations in our galaxy right now. Drake and his colleagues gathered in West Virginia in 1961 to work through the numbers. Their conclusion, even using conservative estimates, suggested between 1,000 and 100 million communicating civilizations should exist in the Milky Way. 60 years later, we've refined some of those variables. We now know that planets are common. We know that habitable zones exist around most stars. We know that the chemical building blocks of life are everywhere. But the other factors remain maddeningly uncertain. How often does life actually start? How often does it become complex? How often does intelligence emerge? And crucially, how long do technological civilizations survive? That last question carries weight. Because if civilizations tend to destroy themselves shortly after achieving the ability to communicate across interstellar distances, that would explain the silence. Perhaps we're looking at a galaxy filled with ruins. Dead worlds where intelligence briefly flickered before snuffing itself out through war, environmental collapse, or technologies that spiraled beyond control. This is the Great Filter Hypothesis, introduced by economist Robin Hanson in the late 1990s. The idea is straightforward but deeply unsettling. Somewhere between the emergence of life and the colonization of galaxies, there exists an evolutionary barrier so difficult that almost nothing gets past it. A filter so fine that it reduces billions of potential civilizations down to the handful we might actually detect. Maybe just one. The terrifying question is where that filter sits. If it's behind us, buried somewhere in our evolutionary past, that's actually good news. It would mean we've already overcome the hardest challenge. Perhaps the jump from non-life to life is extraordinarily rare. Perhaps the evolution of complex cells is a once-per-galaxy fluke. Perhaps intelligence itself is a cosmic accident that almost never happens. If any of those steps represent the great filter, we're through it. We're the exception. But if the filter lies ahead of us, everything changes. Philosopher Nick Bostrom has pointed out that certain discoveries would be catastrophically bad news in this framework. If we found evidence of simple microbial life on Mars, that would suggest life starts easily. If we found fossils of complex organisms, it would mean multicellular life isn't the barrier either. Each discovery that pushes the filter forward in the timeline makes our future prospects darker. Because if life commonly reaches our level of development, and we still see no evidence of spacefaring civilizations, it means something stops them. Something stops all of them. Recent revisions to the Drake equation have attempted to incorporate factors we didn't understand in 1961. A 2024 study examined the geological requirements for complex life and reached sobering conclusions. The researchers argued that plate tectonics, which drives nutrient cycling and creates diverse habitats, may be far rarer than previously assumed. They estimated that less than 17% of planets maintain plate tectonics for the 500 million years necessary for complex life to evolve. When combined with requirements for optimal water coverage and continental land masses, the fraction of truly habitable worlds drops dramatically. By their calculations, the odds fall to somewhere between 0.003% and 0.2% of potentially habitable planets. That's not good news. That's a statistical massacre. If they're right, Earth might not be rare. Earth might be impossible. Meanwhile, we keep searching. The search for extraterrestrial intelligence, SETI, has been scanning the skies for artificial signals since the 1960s. For decades, the effort was modest, using perhaps 24 to 36 hours of telescope time per year. Then in 2015, Breakthrough Listen launched with $100 million in funding and access to the world's most powerful radio telescopes. The Green Bank Observatory in West Virginia, Parkes Observatory in Australia. Thousands of hours of observation annually, examining millions of frequency channels, searching for anything that doesn't fit natural patterns. They've found nothing. Some argue this means nothing itself. Searching for alien signals with current methods is like dipping a cup into the ocean and concluding fish don't exist because your cup came up empty. The galaxy is vast. Radio signals degrade over distance. We might be looking at the wrong frequencies, using the wrong methods, examining the wrong parts of the sky. A 2026 study suggested we may have been searching incorrectly all along. SETI has focused on narrowband signals, assuming alien civilizations would transmit clean, focused beams. But recent research indicates that space weather, solar winds, and coronal mass ejections around distant stars could distort signals before they ever leave their home systems. The effect is strongest around M-dwarf stars, which make up 75% of the galaxy and are prime targets for habitable planet searches. We might be deaf to their transmissions not because they don't exist, but because the universe itself is scrambling the message. Or perhaps they're not transmitting at all. Perhaps advanced civilizations abandon radio communication entirely, switching to technologies we can't detect or haven't imagined. Perhaps they're deliberately quiet, hiding from something we can't see. Perhaps they're watching us right now, waiting to see if we survive our own technological adolescence before making contact. At least 75 different solutions to the Fermi Paradox have been proposed, and more emerge every year. Each carries different implications about the nature of intelligence, the structure of the cosmos, and our place within it. Some assume we're rare. Some assume we're first. Some assume everyone else is dead. But one thing remains consistent across every explanation. The silence demands a reason. The absence of evidence, when evidence should be everywhere, requires justification. Either life is far stranger than we imagine, the universe is far more hostile than we thought, or we're fundamentally misunderstanding something about the nature of intelligence and civilization. What we do know is this. The question Fermi asked over lunch in 1950 has only grown more urgent as our knowledge expanded. Every exoplanet discovered makes the paradox sharper. Every year of silence makes it heavier. Somewhere in the dark, an answer waits. Whether we'll recognize it when we find it is another question entirely. The Great Filter stands as perhaps the most unsettling explanation ever proposed. Not because it's complicated, because it's terrifyingly simple. Economist Robin Hanson introduced the concept in the late 1990s, and it's haunted researchers ever since. The logic goes like this. The journey from sterile rock to spacefaring civilization requires passing through multiple critical steps. The origin of life. The development of complex cells. Multicellular organisms. Intelligence. Technology. Interstellar expansion. At least one of these steps must be extraordinarily difficult. so difficult that almost nothing makes it through. We call this impossibly hard step the Great Filter. And it has to exist. The silence of the cosmos demands it. If all these steps were easy, the galaxy should be teeming with civilizations. It's not. Therefore, somewhere in the sequence from chemistry to empire, there's a barrier that almost nothing crosses. The crucial question isn't whether the filter exists. It's where. If it lies behind us, we're extraordinarily lucky. We've already beaten the longest odds in the universe. Perhaps the jump from simple to complex cells is the filter. This transition happened exactly once in Earth's history, took billions of years, and required such a specific sequence of accidents that it might as well be impossible. Astrophysicist Matt O'Dowd identifies this event, eukaryogenesis, as a reasonable candidate. The difficulty of finding new useful proteins for prokaryotes suggests this was evolution's hardest puzzle. If that's the filter, we've won. We're past it. The universe might be full of bacteria and nothing else. We're the exception that proves survivable. But if the filter lies ahead of us, everything changes. Philosopher Nick Bostrom articulated the nightmare scenario with precision. Finding fossilized complex life on Mars, he argues, would be the worst news ever printed on a newspaper cover. Not because alien fossils aren't fascinating. Because they would prove that getting to complex life isn't the filter. Which means the impossible step still waits ahead of us. And we have no idea what it is. Consider the candidates for a future filter. Nuclear war. Engineered pandemics. Nanotechnology running amok. Artificial intelligence optimizing us out of existence. Climate collapse. Resource depletion. Any civilization reaching our level of technology gains the power to destroy itself in dozens of ways, each more efficient than the last. Maybe that's the pattern. Maybe intelligence itself is the filter. Not because thinking is hard, but because thinking civilizations inevitably develop technologies they can't control. The same curiosity that drives scientific progress also creates weapons of total annihilation. The same innovation that builds cities also poisons atmospheres. The same intelligence that reaches for the stars also designs its own extinction. Recent research suggests behavioral factors might be the problem. Paleobiologist Olav Venn proposes that inherited behavior patterns, the instincts that helped species survive for millions of years, become fatal liabilities in technological civilizations. Aggression, tribalism, short-term thinking. These traits worked perfectly when survival meant competing for resources in small groups. They're catastrophic when survival requires global cooperation and long-term planning. We might be hardwired for extinction the moment we develop the tools to achieve it. But there's another possibility. One that doesn't rely on self-destruction. Perhaps the filter isn't about dying. Perhaps it's about staying silent. The zoo hypothesis suggests advanced civilizations know we're here and are deliberately avoiding contact. Like anthropologists observing an uncontacted tribe, they watch without interfering. Maybe there are protocols. Rules. A galactic consensus that young civilizations must develop independently or not at all. It sounds comforting until you think it through. Why would every civilization follow these rules? Why wouldn't even one break the silence? Unless the consequences of contact are so severe that nobody risks it. Unless they know something about first contact that makes quarantine the only rational choice. Or maybe they're not avoiding us. Maybe they're hiding from something else. The dark forest theory, popularized by Chinese science fiction author Liu Cixin, proposes a different kind of silence. If the universe is full of civilizations, but resources are finite and distances are vast, then revealing your location becomes an existential risk. You don't know who's listening. You don't know their intentions. You don't know their capabilities. In a dark forest, the hunter who makes noise dies first. So everyone stays quiet. Everyone hides. The galaxy could be packed with civilizations, all of them terrified into silence, all of them listening for the sound of something moving in the dark. This explains the Fermi Paradox perfectly. It also suggests that our radio transmissions, our deliberate messages to the stars, our bright presence on the cosmic stage, might be the most dangerous thing we've ever done. Then there's the possibility that we're simply looking in the wrong places, at the wrong things, with the wrong assumptions. What if advanced civilizations don't use radio at all? What if they abandoned electromagnetic communication millions of years ago for something we can't detect? Quantum entanglement. Gravitational waves. Technologies we haven't discovered yet. We're searching for smoke signals in an age of fiber optics. Or perhaps they've transcended physical existence entirely. Uploaded themselves into virtual realities where a billion years of subjective experience fits into a second of real time. Why bother with the messy business of interstellar travel when you can create infinite worlds inside a computer the size of a grain of sand? Why colonize the galaxy when you can simulate it? If that's the path intelligence takes, we'd never see them. They're not out there. They're in there. And we lack the sensors to detect a civilization that exists as pure information. Some researchers propose that intelligence might be common, but technological civilization might be rare. Dolphins are intelligent. Octopuses are intelligent. Neither builds radio telescopes. Intelligence doesn't automatically lead to technology. Maybe most smart species take different paths. Maybe they develop rich cultures, complex languages, sophisticated social structures, but never feel the need to manipulate their environment on the scale required for space travel. We assume technology is inevitable. We assume science is universal. We assume every intelligent species will eventually build rockets and computers. These assumptions might be completely wrong. Then there's time. The Milky Way is 10 billion years old. Human civilization is 10,000 years old. Industrial civilization is 200 years old. Radio-capable civilization is 100 years old. We've been listening seriously for maybe 60 years. What are the odds that another civilization exists right now, close enough for us to detect, at exactly the same technological level, using compatible communication methods? The galaxy might have hosted 1,000 civilizations, but they're separated by millions of years. They rose, flourished, and vanished long before we existed. Or they haven't emerged yet. We're shouting into an empty room, but the room wasn't always empty and won't always be empty. We're just alone in this particular moment. This is the timing hypothesis. We're not rare. We're not doomed. We're just early. Or late. Or exactly on time for a universe where civilizations are common but never overlap. Every explanation carries implications. If we're alone, we bear the responsibility of being the only consciousness in the cosmos. If we're not alone but everyone's dead, we need to figure out what killed them before it kills us. If we're not alone but everyone's hiding, we need to understand why. If we're not alone but we can't detect them, we need better tools. The Fermi Paradox isn't just about finding aliens. It's about understanding our place in the universe. It's about recognizing that the silence itself is data. It's telling us something. We just have to figure out what. And the clock is ticking. Because if the great filter lies ahead, we're approaching it right now. Every year we survive is another year we might not have had. Every technological advance is another test we have to pass. We're either already past the hardest part, or we're about to face it. The math doesn't care about hope. Let's run the numbers. The Milky Way contains somewhere between 100 and 400 billion stars. Conservative estimates suggest 1 in 4 has planets. That's 25 to 100 billion planetary systems. Of those, maybe 1 in 5 sits in the habitable zone where liquid water can exist. We're down to 5 to 20 billion potentially habitable worlds. Now factor in age. Our galaxy is 10 billion years old. Earth is 4.5 billion. Life appeared here within the first billion years after formation. Intelligence took 4 billion more. If those timescales are typical, millions of civilizations should have reached our level millions of years before we existed. Millions of years is a long time. In 1 million years, traveling at just 1% the speed of light, a civilization could colonize the entire galaxy. No faster-than-light travel needed. No warp drives. Just patience and basic physics. Send out ships. Those ships arrive at new star systems. Build more ships. Send those out. Repeat. The math is exponential. Even accounting for breaks, setbacks, and long pauses between waves of expansion, 1 million years is more than enough time to fill every corner of the Milky Way. The galaxy should be teeming with evidence of past or present civilizations. Megastructures. Artificial signals. Modified star systems. Waste heat from massive energy consumption. Industrial signatures in planetary atmospheres. Self-replicating probes. Something. We see nothing. That's the paradox in its purest form. Not philosophical speculation. Not abstract wondering. Cold mathematical certainty colliding with absolute empirical silence. One of these things has to give. Either our math is catastrophically wrong, or our observations are missing something fundamental, or the universe operates by rules we don't understand. Frank Drake tried to formalize this in 1961 with his famous equation. N equals R star times Fp times Ne times Fl times Fi times Fc times L. Each term represents a factor in the emergence of detectable civilizations. The rate of star formation. The fraction with planets. The number of habitable planets per system. The fraction where life actually appears. The fraction where intelligence evolves. The fraction that develops detectable technology. The length of time they remain detectable. Plug in optimistic numbers and you get thousands of civilizations in our galaxy right now. Plug in pessimistic numbers and you get one. Us. The equation doesn't solve the paradox. It organizes our ignorance into neat categories. We've made progress on some terms since 1961. Exoplanet discoveries have confirmed that planets are common. The Kepler Space Telescope found thousands. Ground-based surveys found thousands more. We now know that roughly 1 in 4 stars has an Earth-sized planet in the habitable zone. That's not speculation anymore. That's observational data. FP and NE are no longer guesses. They're measurements. But the rest? Complete mystery. We have no idea how likely life is to emerge on a habitable planet. We have one data point. Birth. That's not statistics. That's anecdote. Life appeared here quickly after the planet cooled enough to support it. Does that mean it's easy? Or did we just get lucky on the first try? You can't tell from a sample size of 1. Intelligence is even murkier. Life existed on Earth for 4 billion years before anything remotely like human intelligence appeared. Dinosaurs ruled for 165 million years and never built cities. Countless species came and went without ever developing technology. Intelligence might be a rare accident, a cosmic fluke that happened once in the history of our planet and might never happen again anywhere else. Then there's the lifetime term. L. How long does a technological civilization last? We've been technologically detectable for maybe 100 years. That's a blink. A rounding error. If the average civilization lasts 100 years before destroying itself or going silent, the galaxy could have hosted millions of civilizations that were never contemporaneous with us. They came. They went. We missed them by millennia. Or maybe civilizations last millions of years. In which case, where are they? This is where the great filter becomes unavoidable. Something is filtering out civilizations. Something is preventing the galaxy from being colonized. Either that filter lies behind us and we're incredibly rare, or it lies ahead of us and we're doomed. The candidates for filters in our past are numerous. The origin of life itself might be extraordinarily unlikely. The jump from prokaryotes to eukaryotes took 2 billion years on Earth and might have required a series of near-impossible accidents. The emergence of multicellular life. The development of complex nervous systems. The evolution of tool use. The discovery of fire. Any of these could be 1 in a trillion events that almost never happen. If the filter is behind us, we're safe. We've already beaten the worst odds. We're the lucky ones who made it through. The galaxy is empty because almost nothing else ever gets this far. We can colonize the stars without competition. We can become the first galactic civilization. That's the optimistic interpretation. The pessimistic interpretation is that the filter lies ahead. That every civilization reaches our level and then hits a wall they can't survive. Nuclear war. Bioengineered pandemics. Runaway climate change. Artificial intelligence that turns hostile. Nanotechnology that goes rogue. Resource depletion. Social collapse. Any number of self-inflicted catastrophes that wipe out technological species before they can spread beyond their home planet. This is why finding life on Mars would be terrible news. If we discovered fossils of complex organisms that evolved independently on Mars, it would mean life is common. It would mean the filter probably isn't the origin of life or the evolution of complexity. It would mean the filter is somewhere ahead of us. Something that kills civilizations after they achieve technology but before they colonize space. Philosopher Nick Bostrom calls this the worst news ever printed on a newspaper cover. Because it would mean we're approaching the filter right now. Every year we survive is borrowed time. Every technological breakthrough is another test we might fail. Some researchers propose a different kind of filter. Not a single catastrophic event, but a systematic limitation. Maybe interstellar travel is simply too hard. Maybe the distances are too vast, the energy requirements too extreme, the time scales too long. Maybe physics imposes constraints we haven't discovered yet that make galactic colonization effectively impossible. But that doesn't explain the silence. Even if physical travel is prohibitively difficult, communication should be easy. Radio waves travel at the speed of light. A civilization that wanted to announce its existence could broadcast signals detectable across thousands of light years. We've been doing exactly that, accidentally, for a century. Our television broadcasts, radar installations, and radio transmissions have been radiating into space since the 1920s. Any civilization within 100 light-years with technology comparable to ours could detect us. We've been listening for 60 years with increasingly sophisticated equipment. We've heard nothing that's definitively artificial. SETI has scanned millions of radio frequencies across thousands of star systems. Breakthrough Listen is the most comprehensive search ever conducted, using some of the most sensitive instruments ever built. Still nothing. Maybe we're listening wrong. A 2026 study suggested that stellar activity might distort alien signals before they even leave their home star systems. Solar winds and coronal mass ejections could broaden narrowband transmissions, making them indistinguishable from background noise. If true, we've been searching for signals that can't exist in the form we expect. Or maybe civilizations don't broadcast. Maybe they go quiet deliberately. The dark forest hypothesis suggests that announcing your presence in a potentially hostile galaxy is suicidal. Predatory civilizations might hunt for signals from younger species. The smart move is to stay silent. Hide. Listen. Never transmit. That would explain the great silence. Everyone's hiding from everyone else. The galaxy is full of civilizations holding their breath in the dark, terrified of attracting attention. We're the only ones stupid enough to be shouting. Or maybe they're here and we can't tell. Advanced civilizations might operate on scales or in ways we can't detect. They might have moved beyond radio communication entirely. They might use quantum entanglement or gravitational waves or something we haven't discovered. They might exist as uploaded minds in virtual realities, having abandoned physical space entirely. They might be all around us, invisible because we lack the sensors to perceive their presence. Each explanation raises new questions. Each solution creates new problems. The paradox remains paradoxical. The universe should be full of life and completely silent. Both things can't be true. Yet both things appear to be true. Somewhere in this maze of possibilities lies the answer to where everyone is. But what if the answer isn't hidden somewhere out there? What if it's right here, staring us in the face? Consider this. We've existed as a technological civilization for roughly 100 years. A blink in cosmic time. We've been seriously listening for alien signals for about 60 of those years. That's 60 years out of a universe that's 13.8 billion years old. We've searched maybe a few thousand star systems thoroughly out of 100 billion in our galaxy alone. The numbers don't add up to anything resembling comprehensive coverage. Think of it this way. If you wanted to find someone in New York City, you wouldn't check 3 apartment buildings and declare the city empty. Yet that's essentially what we've done with the cosmos. We've sampled an infinitesimally small fraction of possible locations, frequencies, and signal types. Then we wonder why we haven't found anything. The search paradox runs deeper than simple statistics. We're assuming alien civilizations would use technology we can detect. Radio waves seem obvious to us because that's what we use. But a civilization 10,000 years ahead of us might communicate in ways we can't even conceptualize. They might have abandoned electromagnetic radiation entirely, moved to quantum communication, gravitational wave modulation, something we haven't discovered yet because our physics isn't advanced enough. You're probably wondering how we'd miss something that advanced. Easy. We're not looking for it. Can't look for it. Don't know it exists. A medieval scholar couldn't detect Wi-Fi no matter how sophisticated his methods. He lacks the conceptual framework. We might be in the same position relative to advanced alien communication. There's another problem. Timing. The universe has been around for 13.8 billion years. Complex life on Earth emerged maybe 600 million years ago. Humans for 300,000 years. Technological civilization for 100. The window where we overlap with another civilization at a detectable stage might be vanishingly small. Two ships passing in a cosmic night that lasts billions of years. Imagine two civilizations separated by 10,000 light-years. One broadcasts signals for 1,000 years before going silent. The other listens for 1,000 years but starts 2,000 years after the first civilization stopped transmitting. They never overlap. Never connect. Both conclude they're alone. Both are wrong. Scale that scenario across the galaxy. Across billions of years. The probability of temporal overlap drops towards zero. We might be surrounded by the ruins of dead civilizations and the seeds of future ones. But nobody's home right now. Nobody we can talk to. Here's where it gets uncomfortable. What if the silence isn't about distance or timing or technology? What if it's about survival? The dark forest hypothesis suggests the galaxy is full of civilizations. They're just hiding. Deliberately. Because broadcasting your location is suicidal. The logic works like this. Resources are finite. Civilizations compete for them. Advanced civilizations might be predatory. They might eliminate potential competitors before those competitors become threats. In this scenario, the smart move is to stay dark. Silent. Invisible. Never transmit. Never reveal yourself. The civilizations that broadcast are the ones that get wiped out. We're the idiots shouting in the forest full of hunters. This creates a selection effect. The only civilizations that survive long enough to become detectable are the ones that never become detectable. They've learned the fundamental rule. Silence equals survival. We haven't learned that rule yet. We've been broadcasting our presence for a century. According to dark forest logic, we've already made a fatal mistake. We just don't know it yet. But there's a flip side to this scenario that's equally disturbing. What if we're the predators? What if we're the civilization other species are hiding from? We tend to think of ourselves as peaceful explorers. But our history suggests otherwise. We've driven countless species to extinction on our own planet. Wiped out entire cultures. Consumed resources without regard for sustainability. An objective observer might conclude we're dangerous. Worth avoiding. That raises an ethical question we're not ready to answer. If we found another civilization, what would we actually do? Study them peacefully, or exploit them? Our track record doesn't inspire confidence. Maybe other civilizations have encountered species like us before. Maybe they've learned to recognize the warning signs. Rapid technological growth, high resource consumption, aggressive expansion. Maybe when they see those patterns, they go dark. Wait for us to burn out or destroy ourselves. There's another possibility that doesn't require predatory civilizations or cosmic paranoia. Maybe advanced societies simply lose interest in communication. Think about human development. We start out desperately social, forming tribes, building cities, creating global communication networks. But as technology advances, we increasingly retreat into virtual spaces, customized realities, personalized experiences. We're more connected than ever and more isolated than ever. Extrapolate that trend forward 1,000 years. 10,000 years. Maybe advanced civilizations turn inward. Upload themselves into virtual realities where they can create perfect worlds customized to their preferences. Why explore the physical universe when you can build better ones in simulation? Why communicate with alien species when you can design ideal companions? Why colonize distant planets when virtual space is infinite and free? This is the transcension hypothesis. Civilizations don't expand outward into space. They expand inward into increasingly sophisticated simulations. They abandon the physical universe entirely. From the outside, they simply disappear. Their planets go dark. Their signals stop. They're still there, in a sense. Just not in any way we can detect or interact with. They've transcended physical reality. If this is true, the galaxy might be full of abandoned planets. Empty shells where civilizations once lived before moving into digital existence. We're scanning the cosmos for signs of life. But life has left the building. Gone somewhere we can't follow. Not yet, anyway. Here's the truly unsettling part. Maybe that's our future too. Maybe every civilization reaches a point where virtual reality becomes preferable to actual reality. Where simulation is indistinguishable from and superior to the physical world. When that happens, why would anyone stay? Why would anyone care about the stars? The progression seems almost inevitable. Better technology leads to better simulations. Better simulations lead to preference for simulated existence. Preference leads to abandonment of physical reality. The universe empties out. Not because civilizations die. Because they leave. This connects back to the simulation hypothesis in unexpected ways. If advanced civilizations routinely move into simulated realities, then statistically speaking, we're probably in one too. The number of simulated realities would vastly outnumber base reality. The odds favor simulation. Which means the Fermi Paradox might have a simple answer. We don't see other civilizations because this isn't base reality. It's a simulation. Possibly one running without other civilizations included in the parameters. But let's pull back from that rabbit hole. There's a more mundane explanation that deserves attention. The rare Earth hypothesis suggests that while simple life might be common, complex life is extraordinarily rare. Earth isn't typical. It's a statistical outlier. A perfect storm of favorable conditions that almost never occurs. The requirements are extensive. Right distance from the right type of star. Large moon to stabilize axial tilt. Jupiter-sized planet in the outer system to deflect asteroids. Plate tectonics for long-term climate regulation. Magnetic field to protect against radiation. Stable orbit in a relatively quiet galactic neighborhood. The list goes on. Each requirement is individually unlikely. Together, they might be vanishingly rare. Recent geological studies support this view. That 2024 research on plate tectonics revised the Drake equation dramatically downward. When you factor in the need for stable continents, optimal water levels, and long-lasting plate tectonics, the number of planets capable of supporting complex life drops by orders of magnitude. Maybe from billions to dozens. Or fewer. If Earth-like planets are that rare, the Fermi Paradox solves itself. We don't see other civilizations because there aren't any. Not in our galaxy. Maybe not in the observable universe. We might be genuinely alone. Not because civilizations destroy themselves or hide or transcend. Simply because the conditions necessary to create them almost never occur. We won the cosmic lottery. The only winners. Maybe the only players. That possibility deserves serious consideration. Not because it's comforting. It isn't. Being alone in the universe is terrifying in its own way. But because the evidence increasingly points in that direction. But here's what makes this truly unsettling. The geological requirements aren't just difficult. They're fragile. Earth barely made it. Our plate tectonics could have stopped. Our moon could have been knocked away. Our magnetic field could have collapsed. We're not just rare. We're lucky. Improbably, astronomically lucky. And that luck had to hold for 4 billion years. Think about what that means for the search. We're not looking for civilizations that overcame unlikely odds. We're looking for civilizations that won the lottery repeatedly. Every single time. For billions of years. Without failing once. The probability doesn't just decrease. It collapses. Some researchers push back against this view. They argue we're making the same mistake humans always make. Assuming our path is the only path. Yes, Earth has plate tectonics. But maybe other geological processes work just as well. Different mechanisms producing similar results. We can't know because we have a sample size of one. Fair point. Except the physics doesn't care about our philosophical preferences. Certain processes require certain conditions. Nutrient cycling needs tectonic activity. Atmospheric regulation needs outgassing. Climate stability needs feedback systems. You can't hand-wave away the requirements just because they're inconvenient for your theory. The rare Earth hypothesis gains support from another angle. Time. Complex life took an extremely long time to develop on Earth. Single-celled organisms appeared relatively quickly, within the first billion years. But complex multicellular life, that took another 3 billion years. 3 billion years of nothing but bacteria and archaea. If Earth is typical, that delay is normal. Standard. Expected. Now consider the lifespan of stars. Sun-like stars last about 10 billion years. Earth needed 4.5 billion to produce technological civilization. That's nearly half the available time. The window is narrower than it first appears. Start the clock a billion years later and we don't make it. The sun becomes a red giant before humans evolve. This timing constraint eliminates vast numbers of candidates. Any planet around a star that formed recently doesn't have enough time. Any planet that took longer than Earth to develop complex life runs out of clock. The viable window shrinks dramatically. But wait. What about planets around older stars? Stars that formed when the universe was younger? They'd have more time, right? Actually, no. Early universe chemistry was different. Fewer heavy elements. Less carbon, nitrogen, oxygen. The building blocks of life were scarce. Rocky planets were rare. The first generations of stars probably couldn't support life as we know it. The Goldilocks zone isn't just spatial. It's temporal. Too early, wrong chemistry. Too late, not enough time. There's a narrow window in cosmic history when conditions align. Maybe we're in that window. Maybe we're among the first civilizations to emerge. Not because we're special. Because the universe itself wasn't ready until recently. This connects to something called the Gaian bottleneck hypothesis. It suggests life might appear quickly but rarely becomes complex enough to maintain planetary habitability. Simple life can actually make planets less habitable. Early photosynthetic organisms produced oxygen, which was toxic to most life at the time. Earth's own biosphere nearly poisoned itself. We survive by luck and adaptation. Most planets might not. The hypothesis argues there's a critical transition. From simple life that destabilizes environments to complex life that regulates them. Earth made that transition. Developed feedback systems. Created a stable biosphere. But the path is treacherous. Most attempts fail. The planet becomes uninhabitable before complex life emerges. Life kills its own world. If this is true, the galaxy might be full of dead planets. Places where life appeared, thrived briefly, then destroyed its own environment. We wouldn't see any signals because they never made it past single-celled organisms. The filter isn't ahead of us or behind us. It's continuous. Every step requires passing another test. Most fail somewhere along the way. Now, here's where things get uncomfortable. Even if we accept that Earth-like planets are rare, there's still a numbers problem. The universe is so vast that even vanishingly small probabilities produce large numbers. If only 1 in a billion stars has a planet like Earth, that's still hundreds of planets in our galaxy alone. Millions in the observable universe. Where are they? This is where the timing argument returns with force. Maybe they exist. Maybe they're out there. But space is big. Really big. And light is slow. A civilization 50,000 light-years away might be broadcasting right now. We won't hear them for 50,000 years. They won't hear us for 50,000 years after that. The conversation delay is longer than human civilization has existed. Even worse, civilizations might not overlap. We arose. We'll broadcast for some period. Then we'll either transcend, collapse, or go silent. The window when we're detectable might be tiny. Thousands of years in a universe billions of years old. Other civilizations have their own windows. The odds of those windows overlapping are minimal. We're all shouting into the void, just at different times. Imagine a cosmic waiting room where civilizations appear one at a time, separated by millions of years. Each one looks around, sees nobody, concludes they're alone. Meanwhile, the previous civilization died out eons ago. The next one won't emerge for eons to come. Everyone is correct. They are alone. Just not uniquely alone. This possibility is somehow more melancholy than actual solitude. It means the universe has produced countless civilizations. They've all wondered the same question. They've all reached the same conclusion. And they were all wrong. The galaxy teems with life. Just never at the same time. Never close enough to connect. Consciousness emerging and fading like fireflies in the night. Beautiful. Brief. Isolated. But perhaps the most challenging aspect of the rare Earth hypothesis isn't about planets at all. It's about observers. We exist. Therefore, Earth-like conditions must be possible. We can't observe a universe where we don't exist. This creates a selection bias. We necessarily find ourselves in circumstances compatible with our existence, even if those circumstances are wildly improbable. This is the anthropic principle. It doesn't explain why Earth is the way it is. It just notes that observers will always find themselves in observer-compatible environments, no matter how unlikely. If the odds of Earth-like planets are 1 in a trillion, and only those planets produce observers, then all observers will inevitably conclude their planet is typical. Even though it isn't. The anthropic principle frustrates scientists because it's unfalsifiable. It explains everything and nothing. Yes, we exist in a universe compatible with our existence. But that doesn't tell us whether such universes are common or rare. Whether we're typical or exceptional. It's a logical tautology dressed up as explanation. Still, it matters for the Fermi Paradox. If Earth-like conditions are required for observers, and such conditions are extraordinarily rare, then the absence of other civilizations makes sense. Not because civilizations are impossible. Because the preconditions are so specific that very few emerge. We might be one of a handful. Or the only one. In this galaxy. Possibly in the observable universe. That thought should inspire humility. If we are genuinely rare, genuinely improbable, then our existence carries weight. Responsibility. We're not just another civilization among billions. We're potentially the only conscious minds capable of understanding the universe. The only beings who can appreciate beauty, create art, ask questions about existence. If we disappear, that capacity might disappear with us. Forever. The rare Earth hypothesis thus reframes the Fermi paradox entirely. The question isn't why we don't see others. It's why we exist at all. What sequence of improbable events led to this moment? What cosmic dice had to roll perfectly for consciousness to emerge? The answer appears to be more dice than we imagined. Each one loaded against us. And yet we're here. Against all odds. Despite the filters and bottlenecks and requirements and constraints. Somehow Earth threaded every needle. passed every test, survived every catastrophe. 4 billion years of continuous good fortune. An unbroken chain of unlikely events. Which brings us back to the beginning. Fermi's question. If we're this improbable, this rare, this lucky, then where is everybody else? The silence of the cosmos isn't mysterious. It's expected. Inevitable. The universe is vast and ancient and mostly empty. Life is hard. Complex life is harder. Intelligence is harder still. Technological civilization. Rarest of all. We are the exception that proves the rule. The statistical outlier. The improbable result. Not because we're special in any meaningful sense, but because someone had to win the lottery. The fact that we exist doesn't mean the odds were good. It means someone beat the odds. This time. This place. Us. But there's another possibility. One that challenges the entire framework. What if we're asking the wrong question? The Fermi Paradox assumes civilizations want to be detected. That they broadcast signals. Build megastructures. Expand across galaxies. Leave obvious traces. But why would they? Consider our own trajectory. We've broadcast radio signals for barely a century. Already we're moving toward quieter technologies. Fiber optics instead of radio. Directed communications instead of omnidirectional broadcasts. Encrypted data instead of clear signals. Within another century, Earth might go radio silent. Not because we collapsed. Because we evolved beyond noisy technology. Advanced civilizations might do the same. They exist. They're out there. But they're not shouting into the void. They're using technologies we can't detect. Communication methods we haven't imagined. Energy sources that don't leak radiation across space. The universe could be teeming with civilizations. All invisible to us. Not hiding deliberately. Just operating on frequencies we're not tuned to. Using physics we don't understand yet. This is the dark forest hypothesis. Proposed by Chinese science fiction author Lu Cixin. The idea is simple but chilling. The universe is a dark forest. Every civilization a silent hunter. Broadcasting your location is dangerous. It invites predation. Competition. Conflict. So everyone stays quiet. Listening. Watching. Hoping not to be noticed. If this is true, Earth's radio broadcasts were catastrophically naive. We've been screaming our coordinates into the darkness for decades. Announcing ourselves to anything listening. Maybe the silence isn't mysterious. Maybe it's strategic. Every civilization that survives learns the same lesson. Don't make noise. Don't draw attention. Stay hidden until you understand the rules. The dark forest might explain everything. Why SETI hears nothing. Why we see no Dyson spheres. Why the galaxy appears empty despite being potentially full. But it raises another question. If staying silent is the survival strategy, why haven't we been warned? Unless we have been. And we're not listening. There's also the zoo hypothesis. The idea that Earth is deliberately being avoided. We're a nature preserve, a protected site. Advanced civilizations know we're here. They watch, but they don't interfere. Like wildlife biologists observing animals without revealing themselves. Letting natural development proceed uninterrupted. This seems anthropocentric. Why would aliens care about contaminating our development? What makes us special enough to preserve? Perhaps nothing. Perhaps it's standard protocol. Don't interfere with emerging civilizations until they reach a certain threshold. Develop certain capabilities. Demonstrate certain characteristics. We haven't passed that threshold yet. So we remain uncontacted. Observed from a distance. Waiting for the moment we're ready. Or maybe it's simpler than that. Maybe we're just boring. Earth is young. Our sun is middle-aged. Many stars in the galaxy are billions of years older. If civilizations arise on planets around those stars, they've had enormous head starts. A civilization even 1,000,000 years ahead of us would be incomprehensible. Their technology would look like magic. Their motivations would be alien. Their scale would be cosmic. Why would such beings bother with us? We're primitive. Barely technological. Still fighting over resources and territory. Not worth the attention. They might observe us the way we observe bacteria. With scientific interest but no real engagement. We're too different. Too simple. Too far beneath their level of development. This is deeply humbling. We assume contact would be momentous. World-changing. But to them, we might be utterly unremarkable. Then there's the simulation hypothesis. The idea that we're not in base reality at all. We're in a simulation. A computer program running on substrate we can't perceive. If true, the Fermi Paradox dissolves. There are no aliens because the simulation doesn't include them. Or it does, but they're in different simulation instances. Parallel universes running on the same computational substrate. Never intersecting. We don't see aliens for the same reason video game characters don't see players in other games. We're in separate instances. Different runtime environments. This sounds like science fiction. But serious physicists take it seriously. The simulation argument has genuine philosophical weight. We can't prove we're not simulated. And if we're not, we might create simulations ourselves eventually. Which means simulated realities could vastly outnumber base reality. Statistically, we're more likely to be in a simulation than not. But even if true, it doesn't help much. Simulated or real, the silence remains. The absence persists. We're still alone in our observable environment. Each explanation for the Fermi Paradox tells us something different about the universe. And about ourselves. If we're rare, we're precious. Our existence is a cosmic accident worth protecting. If we're early, we have responsibilities. We might be the first intelligence to spread across the galaxy. The ancestors of future civilizations. If we're filtered, we're fragile. Our survival is uncertain. The path ahead is dangerous. If others are hiding, the universe is more dangerous than it appears. Silence is survival. If we're ignored, we're insignificant. Our cosmic importance is zero. If we're simulated, reality is stranger than we imagined. Nothing is what it seems. None of these answers is comforting. All of them challenge our assumptions, force us to reconsider our place in the cosmos. But maybe that's the point. The Fermi Paradox isn't meant to be solved. It's meant to make us think, to confront the implications of an apparently empty universe, to wrestle with the meaning of our existence. Because here's what we know for certain. We exist. Against incredible odds. Despite countless filters and barriers and requirements. We're conscious, self-aware, capable of understanding the universe, of asking questions about our place in it. We've built telescopes that see billions of light years, spacecraft that leave the solar system, theories that explain the fundamental nature of reality. We've created art and music and literature, languages and cultures and civilizations. We've loved and suffered and persevered. All of this happened on one small planet orbiting an average star in an unremarkable galaxy. Whether we're alone or not, whether others exist or ever existed, whether we're first or last or only, none of that changes what we are, what we've accomplished, what we might become. The silence of the cosmos doesn't diminish us. It defines our moment. Right now. This instant. We're the ones asking. The ones listening. The ones reaching out. Maybe someday we'll hear an answer. A signal from across the stars. Proof that we're not alone. Or maybe we won't. Maybe the silence continues forever. Maybe we really are the only ones. Either way, we have a choice. We can see the silence as tragic, empty, meaningless. Or we can see it as an invitation, an open universe, waiting for us to fill it. The Fermi Paradox will remain unsolved. Perhaps forever. But the question it asks endures. Where is everybody? And the answer, whatever it turns out to be, will reshape everything we thought we knew about existence itself. We stand at a peculiar moment in history. The first species on Earth capable of asking whether we're alone. And possibly the only species in the galaxy doing the asking. That's the weight we carry. Not certainty. Not answers. Just the question itself. Echoing through an apparently empty cosmos. 75 years since Fermi posed his simple query. Decades of searching. Thousands of exoplanets discovered. Billions spent on telescopes and receivers. Mountains of data analyzed. And still, nothing. No signals. No structures. No evidence whatsoever. The silence grows heavier with each passing year. Each new discovery that makes the paradox sharper. Each habitable planet found that should host life but apparently doesn't. We've explored the explanations. Rare earth. Great filters. Dark forests. Simulations. Timing mismatches. transcended civilizations. Each theory explains part of the puzzle. None explains all of it. Perhaps that's because there isn't one answer. Perhaps multiple factors combine. Life is rare and civilizations destroy themselves and survivors hide, and we're looking in the wrong places using the wrong methods at the wrong time. Or perhaps the answer is simpler than we want to admit. Perhaps we really are alone. The only consciousness in a universe of matter and energy. The only beings capable of understanding what we're part of. The only voices in the void. That possibility terrifies us. So we keep searching. Keep hoping. Keep building better instruments and refining our theories. Because the alternative, accepting that we're truly alone, feels unbearable. But maybe it shouldn't. Maybe being alone isn't tragic. Maybe it's profound. If we're the only ones, then everything we do matters. Every choice. Every action. Every moment of compassion or cruelty. There's no one else to pick up the pieces if we fail. No other consciousness to appreciate beauty if we destroy ourselves. No backup copy of intelligence in the universe. We become infinitely precious. Irreplaceable. The universe's only way of understanding itself. Its only source of meaning. Art. Love. Questions about existence. All of it depends on us. All of it ends with us if we're not careful. That's not a burden. That's purpose. Responsibility on a cosmic scale. We're not just another species fighting for survival. We're potentially the only species that can contemplate survival. Plan for it. Choose it deliberately. The Fermi Paradox forces us to confront that reality. Either we're alone and everything depends on us, or we're not alone and we need to figure out why we can't detect anyone else. Both scenarios demand we take our existence seriously. Stop treating Earth like an expendable practice run. Recognize that this might be it. The only shot. The only world capable of supporting consciousness anywhere in the observable universe. Somewhere out there. Maybe. Other minds might be asking the same questions. Staring at their own empty skies. Wondering why they hear nothing. Concluding they're alone. Just like us. If so, we're connected by that shared solitude. That universal question. Separated by distances too vast to ever cross. By time scales that prevent overlap. By technologies incompatible with communication. But asking nonetheless. Or we're genuinely alone. The first. The only. The last. And that means every sunset we observe. Every equation we solve. Every story we tell. Every hand we hold. It all matters more than we can possibly comprehend. Because if we disappear, that's it. The universe returns to unconscious matter. No one left to notice. To care. To remember. The search continues. It has to. We can't stop asking. Can't stop looking. Even if the answer never comes. Even if the silence persists for millennia. Because the question itself is what makes us human. What makes us conscious. What makes us matter? Where is everybody? We don't know yet. Maybe we never will. But we're here. Right now. Asking. And that might be the most important thing in the universe.